In this video, we're going to begin to talk about work and energy and how the two relate. So first, let's talk about what work is. Well, work is a force that is exerted over a distance. And in order for an object to exert a force over a distance, it will take an amount of energy. And so if we exert 1 Newton over 1 meter, that converts to 1 joule of work. Some of the other units of work would be foot-pound in the British system or an erg in the centimeters grams system. We'll typically just use joule when we talk about our standard system here. A Newton times a Newton meter is a joule. So one of the key things to remember here is that when we exert a force, in order to have work, the force must be in the direction of the displacement. And so we'll have to break our force into its components when we have a force up at an angle. And so we can rewrite that force equation to say that really the work, instead of just the force times the displacement, it's really F cosine theta times the displacement. And we get cosine because when we have the angle between our force and our displacement here, using cosine, that gives us the parallel portion of the force. And so that's what we want to use. Now, keep in mind, cosine of 0 is equal to 1. Cosine of 90 is equal to 0. So if we are perpendicular, if we have a force perpendicular to our displacement, there is no work being done. And if we have a force that is 180 degrees away from our displacement, we get a -1, which means we get a negative work. And that sign means something here. So we have to pay attention to the sign of the work, whether it's positive or negative. So here's an example. We have someone pulling on a suitcase, and we want to find the work done if the force is 45 newtons, the angle is 50 degrees, and the displacement is 75 meters. Now, if we were just pushing with 45 newtons in the direction of our displacement, we would simply multiply these two numbers together, and that would be our work. But since we're at an angle, we have to use cosine of theta, which in this case is cosine of 50 degrees, multiply the three together, and we get 2,170 joules. One thing to keep note here is we got to make sure our calculator is in degrees, not in radians. And another thing to mention is just pulling this suitcase with a pretty small force, 45 newtons is not a very big force, we get 2,000 joules. So this gives you a little bit of an idea of how big a joule is. A joule, even though it's the standard unit of measure for work, is actually a very small amount of work. So we're going to get pretty big numbers here, and a lot of times we'll use kilojoules or even mega or gigajoules to talk about our work done. Before I mentioned that cosine of 0 was 1 and cosine of 180 is -1, this is an example of how our work can be positive and negative. So think of someone bench pressing the weight, and as they push the weight up off of their chest, the displacement is vertical, and the force they're exerting is in that same direction. So they're doing positive work on the weight to move it vertically. And so since the angle between them is 0, they're doing positive work, the force they exert times the displacement. Whereas when they lower the weight, when they go from the fully extended arms down to the weight being on their chest, the displacement is in the opposite direction of the force, and so we consider that work to be negative because the directions are opposite. There's 180 degrees between them. And when we relate this to energy, it'll start to make a lot more sense and why we have to have this relationship of positive and negative. So let's look at another example here. We have a truck that is accelerating at a rate of 1.5 meters per second squared. The mass of the crate is 120 kilograms, and it does not slip. So right away, it does not slip. That means there has to be static friction involved. So if we're given a magnitude of the displacement of 65 meters, we want to know what is the total work done on the crate by all of the forces acting on it. Well, let's find the net force on this object first, and to do that we need to draw a free body diagram. So we see that we have the normal force going up, the weight going down, and the frictional force going to the right just because we have our displacement drawn to the right. The angle between the displacement and the normal force is 90 degrees. And the angle between the displacement and the weight is also 90 degrees. So therefore we know the work for both of those are going to be zero. So the normal force is doing no work on this crate, and the weight is doing no work on this crate because their forces are not in the same direction as the displacement. However, the frictional force is doing work, so we can find that by calculating the frictional force, knowing that it's the only force acting on the object. Using Newton's second law, we can do mass times acceleration to get 180 newtons as the frictional force. And if we're going a displacement of 60, multiply the 180 newtons by the 65 meters, and we get 1.2 times 10 to the fourth joules, or 12,000 joules. And like I said before, joules are a very small unit of work or energy, and so we're going to get pretty big numbers here. Now, let's consider a constant net external force acting on an object. And the object is displaced some distance. We can call it S or X. A lot of times those are going to be interchangeable. You've probably seen on some of the diagrams it was listed as S, but in the equations I'll use X. So consider those to be synonymous. And so if the object is displaced a distance in the same direction as the net force, we know that we have this net force in the direction we're saying to the right and displacement to the right. We know that the work done is going to equal the force, that net force, times its displacement. And so we can find the net work just by taking the mass times acceleration times that displacement. Well, if we continue with that, looking at the a times x, well, that a times x, let's go back to kinematics here and look at the kinematic equation when we have a final velocity squared is going to equal the initial velocity squared plus 2a delta x. And this is when we have a constant acceleration. This equation holds up. So if we solve this equation for ax, we find this expression of 1/2 times the difference of the squares in the velocities. So if we substitute that back in, we get this unique result here that the work is equal to 1/2 mv squared, where the v is the final velocity, minus 1/2 mv squared, where v is the initial velocity. And so this right here is what we call the work energy theorem. And this brings in the idea of what is kinetic energy. Well, kinetic energy is basically stating that any object that is moving has energy, and we can quantify that energy with the equation 1/2 mv squared. So if an object has velocity, we square it, multiply by its mass, multiply by 1/2, and we get its kinetic energy in joules. And this is important. This is measured in joules. Well, this right up here tells us that the work on an object is equal to its change in kinetic energy. So this is the work energy theorem. It's telling us that the change in kinetic energy is equal to the work, or the work done on an object is its change in kinetic energy. So if we see that a force does work on an object, we observe that through its change in kinetic energy, or its change in velocity. If the velocity increases, positive work is being done. If the velocity decreases, negative work is being done. Let's look at an example here. We have the mass of a space probe is 474 kilograms, and it has initial velocity of 275 meters per second. If there is a force of 56 millinewtons, so it's a small force, and it displaces over a very large distance of 2.4 times 10 to the 9th meters, what is the final speed? So we're going to use the fact that the work done on the object is equal to the change in kinetic energy. So let's calculate the work first. Well, to calculate the work, we need the net force on the object times cosine of the angle between the force and the displacement times the displacement. So the net force on this is going to equal the 5.6 times 10 to the negative second, or the 56 millinewtons. The angle between the force and the displacement is 0, so that's just going to give us a factor of 1. We multiply by the displacement, that gives us our work. Well, that has to equal our change in kinetic energy, and so our initial kinetic energy is 1/2 the mass times the initial velocity squared, and our final kinetic energy is 1/2 the mass times our final velocity squared. Do some algebra, and we get the velocity to be 805 meters per second. Let's look at a slightly more involved situation. We have a skier skiing down a hill that is elevated at 25 degrees. And so if we look at this skier and we draw a free body diagram, we have the normal force up, we have the weight that's going directly down. Remember, the normal force is perpendicular to the surface of contact, and so the weight is down at an angle of 25 degrees. So we're going to use the coordinate system that has an x-axis parallel to the inclined plane here to simplify things for us. And so that means that our vertical component of weight is mg cosine 25, and the horizontal component of the weight is mg sine of 25. So if we look at the forces along the x-axis here, because along the y-axis they balance out, this skier isn't accelerating off of the slope or into the slope. So we're only looking at the horizontal direction, and that's where we have the sum of the forces, mg sine of 25 minus the kinetic friction, which is back up. So if we were to find the net work on this object, we would have to know the kinetic friction, and we'd have to know the mass, and we'd have to find this net force first, and then multiply by the displacement, because our displacement is in the direction of the slope here, and so we could find our displacement there. Or if we wanted to find the work, we could look at, if we had the known velocities here, we could find the change in kinetic energy and relate that back to the work. One final example here. Let's think of a satellite that is in a circular orbit around the Earth here, and one that is in an elliptical orbit around the Earth. And knowing what we know about the work energy theorem and kinetic energy specifically here, does the kinetic energy change in each of these, or does it not change in either of them? And so looking at the circular orbit, we know we have a constant speed. And with the constant speed, that means our kinetic energy is also going to be constant. However, in the elliptical orbit, we are going to have a higher speed here. So v here is going to be greater when we're closer to the Earth, whereas over here, v is going to be lower. And so we are going to then have a change in kinetic energy. And if there's a change in kinetic energy, that means there has to be work done on the object. And so later we'll talk about gravitational potential energy, and so we'll be able to see what is actually doing the work in this situation. But the key right now is just to see that there is work going on in situation B because our velocity is changing in magnitude, which means our kinetic energy is changing. That also brings up one final point of kinetic energy is not like work in that you cannot have a negative kinetic energy. Kinetic energy is only positive. We don't care about the direction of kinetic energy like we care about the direction of the forces in work. Kinetic energy is a scalar quantity. It only has a magnitude. So we only take the speed of the object, square it, and then multiply by the mass in 1/2, and that gives us a scalar quantity of kinetic energy. Whereas work is a vector, and the direction does matter.